Welcome to Exam Prep 3. In this one, I'm going to do a standard box on a slope. Remember that one where we've got the box on the slope, and they ask us a whole bunch of questions about that. When will it slide? What will happen if it does this? And if I put a tension there, what's the maximum I have to use, etc., etc. So those are the typical questions with elements on a slope. The other one I'm going to do is I'm going to turn it around, and we're going to look at the question where we've got being pulled through the Panama Canal or being straightened in the canal with two locomotives or tugboats or a ship being dragged through the canal. Let's get started. What we've got is we've got a 10 kilo mass on a slope, right? And we know that what we do is we say, right, we go ahead and we draw it, and I didn't want it in blue, so I'm just going to redo that and put it into a black pen. Okay, there we go, cool. So let's just start off and we say, right, this is what they've given us. Now, remember in all of this physics, the secret is to look for the pattern that you've seen before. If you recall, you're either going to see the forces in verticals, horizontals, combinations of the two, but look for the pattern and follow the recipe through. Each and every time, this is the recipe we're going to be following. Let's put our block on the slope. We've got a 10 kilogram block sitting on this slope over here. Never mind what they have said to us. The first thing we do is we put in the weight, which in this case, let me just put in my 10 kilograms there, is mg, which is going to be 98 newtons acting down. What is the next step we do? The next step we do straight away is we complete the component triangle, the 90 degrees there. Our weight is always the hypotenuse, remember? We're coming down like that. So we must make sure that we put in it vertically down towards the center of the earth. That's going to be the hypotenuse. Then we transfer the angle, if we're given it, the 20 degrees over there. Then we go, and now we've got forces at an angle. So we're going to resolve them into their components, aren't we? What are the components? Stand at the angle and say opposite. So that one is going to be 98 times the sine of 20 degrees. This one is going to be 98 times the cos of 20 degrees. And that's going to give us equal to 92.1 newtons. And this one over here is going to be 33.5 newtons. Then we take the one that is parallel to the slope, and we put that on the block like that. 33.5 newtons. Then the last is we put in F normal. F normal is 92.1 newtons. There's my F normal. Right, so we've done our, we've basically done our prep work. So now we can take it to the next step. The second part of the recipe is we say, right, we've put in our forces perpendicular to the slope like that, and parallel to the slope, which is the one that's pulling it down. Then we look, have they given us friction? In this case, yes, they said mu equal to 0.15, right? Therefore, we go ahead and we calculate frictional force equal to 0.15 times F normal, which is 92 newtons. I'm just rounding it down to 92, okay, just to keep it a little easier. Then we calculate it, 0.15 times 92 is going to be 13.8 newtons. And there we've got our force of friction, which is now we're going to say, okay, what is this block going to do? Well, hang on. You have a block. You have a slope. What does the block want to do? It wants to slide down, right? So what is holding it in place? What's holding it in place is the friction between the two surfaces. As you can see, look, it's not sliding. Yeah, there she goes, you see? Not sliding. There she starts going. So the friction is what's holding it in place, isn't it? And it doesn't matter how they ask these questions. This is the recipe to follow for it. So right, now we say, okay, the first question is, what will happen to the block? Well, what do we do? Let's move that up slightly. We say, all right. Now, let's just take a look at our block again, just quickly, right? and I'm just putting it in terms of, remember, the block at this stage has got a force of 33.5 newtons acting down the slope, hasn't it? That's the component parallel to the slope which is wanting to pull the block down that slope. But now what is acting against that? We just said force of friction. And force of friction is 13.8. So what have we got? Let's think. We've got a force pulling down the slope of 33.5 and a force acting up the slope that way, pulling there, of only 13.8. In other words, the one pulling down is bigger than the one trying to pull up, which means the block's going to want to slide down the slope, isn't it? It's going to want to go that way because there's not enough friction. That's as simple as that. So in this case, we've got an unbalanced force. Remember, unbalanced force is F net. So we say F net is going to be equal to, and it's going to be equal to 19.7. Let's just see how much. 33.5 minus 13.8, which is going to be equal to 19.7 newtons. And remember, you have to put in which way it's going, down the slope. All right? What do we say? The moment you've got an F net, you go to MA, and we say 19.7 equals, because remember, F net equals MA. 19.7 newtons is going to be equal to 10 times A. Therefore, A is going to be equal to 1.97 meters per second squared. And once again, down the slope. And remember, the moment you see any F nets, you've got to go for that acceleration. Because there could be a linked question to this, right? What will the velocity be at the bottom of the slope, or whatever the case might be? Because they can link in the different questions. But at this point in time, let's just say we've sorted that out. So there's no other forces on the block. The next question is they ask us, right, just for argument's sake, let's say they ask us, what is the tension needed to keep the block in place? Now what have we got? Once again, let's go back to my blocks. Here's my arm. So here we've got this situation. Get that to stay stable. And there we've got, but now we've got a tension, right? In other words, now when it wants to go, I can hold it up. I can balance the force up the slope, can't I? So what have I got? Let's have a look at it, right? Once again, we've got this here. We've got the block, and this is the 33.5 newtons. Now, there's a T there. And they've asked us, what is the tension needed to just keep the block in place? Which means we've now gone to equilibrium, isn't it? Think about it. They've asked us the minimum tension. Just visualize what's happening there. The block wants to slide down. So, in other words, friction is acting up. Friction is acting up, and it's 13.8 newtons. So the tension over there, the tension up the slope that we're pulling, and the friction, we're helping each other, right? I'm not pulling a block up the slope, it's not moving, but I'm just basically balancing it out, right? So what do? I say, okay, there we go. Let's see. So therefore, T plus 13.8 must be equal to 33.5. So T is going to be 33.5 minus 13.8. And let's just get that quickly. 0.5, 13.8. Okay, what have we got there? That's going to be 2, and that's going to be 5. Oh dear, 7. Right? I really don't enjoy doing it in my head anymore, hey? So that's gone to a 2 now. And that's going to be 3 from 12 is going to be 9. So it's going to be 19.7. Sorry, my bad. 19.7 newtons. Right? So what have we got there? We've got 19.7 newtons. Okay? The next question, in other words, that's the force that I can put just to hold the block in place. The next question is, okay, what's the maximum force that we can use? Well, same principle. There's T again. There's our 33.5 down the slope. But now what happens? The maximum is, I am now going to start pulling the block up, which means friction is going to reverse, isn't it? So we're going to get FF down here is going to be equal to 13.8. Therefore, T is going to be equal to, unbalanced force, right? Because, equilibrium still. No unbalance at this stage. T is going to be equal to 33.5 plus 13.8, which gives us 47.3 newtons up slope. Okay? Very important. We've now got, remember in the middle there we had two equilibrium situations. The one is where the tension and the friction are balancing the pull down the slope. This one is the friction has turned around because now I'm starting to pull it up the slope. So my friction's acting the opposite way. Okay? This is just logicking it out, asking yourself what's going to actually happen here. Right? So I can put 47.3 newtons of force up the slope. What happens if I exceed that? That's the next question. The next question is, right, they say to us, now, what will happen if we put in a 50 Newton force? (33.5) and FF still is 13.8. So what have we got? 50 upslope, and we've only got the sum of those two, the 40 odd, 47.3 down the slope. So there's more force up than down, which means we're going to have an F net, which is going to be 50 minus 33.5 minus 13.8, which is going to give us an F net of 2.7 newtons. F net goes straight to MA. 10 times A, therefore the acceleration is going to be, in this case, 0.27 meters per second squared up the slope. Okay? All of those, in essence, all they are they're just logicking it out, right? And it doesn't matter if it's downhill, uphill, whatever, even horizontal. Just follow the steps through it, all right? Putting in what you know and what you've been given. The next one, they say we've got, this is one of the questions I put onto the sheets. We've got a ship, okay, and I'm really, once again, I'm not an artist, guys, I really am not. I'm an engineer, and art was not my bag. So what we've got is we've got over here, we've got A, okay, and we've got B pulling, and I've drawn it not perfectly well because my angles are a bit out, and they say that they are pulling this ship at a constant velocity of 0.5 meters per second. Okay, what does that mean? This is either tugboat B or locomotive B if you've watched the new Panama Canal. What we've got here is the old Panama. Sorry, they had the locomotives on the side. The new one, they've got a bit of an argy-bargy going about this because they're not there anymore, and a lot of the captains are a bit worried with the size of their ships going through. We are pulling at a constant velocity of 0.5 meters per second. What does that mean? Well, it's actually very important because we are at equilibrium. Constant velocity, equilibrium. Why? Let's just recap. F net equals MA. At constant velocity, A is 0. Therefore, F net is M times 0, which is 0. There is no F net if we are traveling at a constant velocity. Okay? Right. So, let's take this problem. Can you see it's just basically in plan, as opposed to the strings this way or the strings that way in equilibrium, but it's in equilibrium. So what do? Well, the first thing we always do in equilibrium is we resolve forces into their horizontal and vertical. So I'm going to call this over here tension in rope A and tension in rope B. You know how this works already. I mean, that's what we do for each one. Let's have a look at rope A. So what do we do? Okay, we've got TA over here, and that's 40 degrees. So you know, force at an angle, what must we do? Resolve into vertical and horizontal components. That is TA, let's make it capital A, sine of 40 degrees. And this one is TA cos of 40 degrees, right? Then we say, right, TA cos 40, that's 0.766 times TA. And this top one is TA sine 40 degrees is 0.6428 times TA. And yeah, I do it to 4 decimal places. I do it in stoichiometry the same way in chemistry. I don't really cut it back, but you know, they will tell you what they want you to do with it. But I just use 4. I reckon it's fun. So we've got that. Now let's look at force B, shall we? I'm just going to change it to, let's call it green, guys. Eh? Before I do that, let's just draw in the force itself. We've got a force TB, which is down here. And TB is going to be at an angle of, we said 30 degrees down there, right? So let's go and put in the components of this one. There we go, like that. Once again, this is TB sine of 30 degrees, and this is TB cos of 30 degrees. And let's see what those, I've just done it ahead of time. TB sine is 0.5. Okay, TB cos is going to be 0.866. Like so. Now, once again, and I'm sure you're tired of me repeating it, but it's equilibrium. Total up equals total down. Total to the right equals total to the left. So that's what we do when we're in equilibrium. Let's just follow the recipe and do that, shall we? Let's put the total, now in this case it's not up and down, but it's the total to that way. Let's say north and south, east and west, right? Okay, let's just go back to my normal color. And right, if I put the total to the north and south, right, north and south, which is actually in this plane now, what are we doing? We are saying that, in that case, 0.6828 times TA must be equal to 0.5 times TB. Remember, what did we do here? We put these forces here. That one was that way. I put it equal to that one, correct? We're putting the two forces that are acting north and south opposite each other. We put them equal to each other. And then we know we're going to get two simultaneous equations. What I've done is I've written it as TB is going to be equal to 1.2856 times T of A. I just divided through by 0.5, okay, to make TB the subject of the formula. The next thing is, well, just before we move on, let's just take a quick look at this concept here. Can you see here that TB is 1.2856 times TA? That means that whatever the system gives us for tensions, what it means is that TB is always going to be bigger than TA, which means if you've got a limiting force, it means that TB is going to be the limiting force. Because, for example, if TA is 100, TB is going to be 128, isn't it? There is where we look to see if a force is going, or a tension in a cable can get too high, right? Just remember that concept. We've got the one is a multiple of the other one, right? Now we put the two horizontals. Let's just give ourselves a bit of space. Let's put the horizontals. We say, all right, the horizontals, or the easts and the wests in this case, was 0.766 TA plus 0.866 TB must be equal to 100,000 newtons. Let's just go back and recap it so that we can see what we're doing. Okay? Can you see what I've done? Look at this. This one is acting that way. This one is acting that way. This 100,000 was the frictional force or the drag on the boat. Okay? Which is obviously acting the opposite direction to movement. Same as friction. Friction and drag, same thing. So I've put the total acting, let's say that way, to the right, okay, equal to the drag, which is now pulling me back to the left. Let's just finish it off, because now it's basically, you just rewrite TB in terms of TA, and all I can advise you at this point is, do you know what? Just take your time. I know time is not always of the, you haven't always got loads of it, but put them in neat 1.2856 times TB, my bad, sorry, TA, okay, like so, is equal to 100,000 newtons. I'm not going to go through the whole thing. You get 1.879 TA equal to 100,000. TA comes out to be equal to, in this case, TA 53,220. And you put it back in, back substitute, TB 68,419 newtons, right? Now, for example, if they could have asked the question in a slightly different way. They could have looked at it and said, okay, let's do it with, let's say, maybe they gave us the maximum braking strain. Then we would say, aha, they've given us TB, remember? TB is the maximum one. So they've told us how much TB can be, so I'd work backwards from TB, find TA, then I'd go backwards and eventually maybe find the drag, the frictional drag on the boat, whichever way they ask the question. But the essence of it is the recipe is exactly the same, whichever way we look at it. You just equilibrium, total up, total down, and when we got or right and left as well, or when we've got a situation where we've got forces that are in plan like this one, north, south, east, west, right? But they're always going to be equal to each other because there's no F net. It's only on an object where there's a force that's not accounted for, it's unbalanced, that we get an F net. Okay. Thanks for watching that one. I hope you guys went through it. Please go through it again and have a look at what we've done. Make up one of your own, you know. Nothing wrong with that. Make up one, just give it an arbitrary friction or give it a drag or whatever the case might be. Or you know what, turn the strings the other way around on the 3-string problems. Instead of them acting this way, that way, go up and down instead. You never know. It's the same recipe and it's just have some fun with the numbers.